This is but one satellite in a continuous development series to be launched in the Air Force space program. The Air Force concept of a long-term satellite launch series included the buildup of a development effort to qualify a versatile family of highly advanced satellite vehicles for equally advanced space applications. The time is T-minus 25 minutes. To get some sense of the vast effort that places this space vehicle here at T-minus 25 minutes, we must turn the clock back to T-minus 25 months. The beginning is here at Lockheed Missile and Space Division's Sunnyvale headquarters, prime contractor to the Air Force for the overall satellite system project, of which Discoverer is but one facet. It is one of the largest industrial complexes of its kind, designed to accommodate exclusively the development of space-age products. The immense planning effort that created the far-reaching space programs involving the Agena satellite is now history and a separate story. Obviously, the planning was well guided, for the vehicles already orbited speak for themselves. The years of careful planning first resulted in a satellite production line to provide a basic satellite vehicle adaptable to a variety of space missions. Under the guidance and direction of the Air Force Ballistic Missile Division, the development effort swiftly grew to the point where a steady flow of qualified space vehicles has become possible. The vehicles must do their jobs consistently with great precision and high reliability, well out of the reach of any repair service. Consequently, many exacting inspections are required during each step of the fabrication. As the individual components come off the line, they are assembled in special jigs, where each operation is controlled by delicate optical alignment techniques. Here, too, each individual wire is tested in a comprehensive circuit analysis that verifies the performance not only of each wire, but the electrical system as an integrated whole. Thus, hundreds of pieces of metal, wire, and plastic, cold, impersonal bits of hardware take shape, and to the men who built it, the satellite assumes a personality. The Discoverer satellite vehicle is nearly 20 feet long, 5 feet in diameter, and weighs close to a ton, minus payload and fuel, and is powered by a compact rocket engine designed and built by Bell Aircraft Company. Until the Air Force orbited Discoverer 1, United States satellites were comparatively small, weighing under 100 pounds. The notable exception was, of course, Project SCORE, in which an entire Atlas ICBM was orbited. With Agena, we are concerned with the development of a series of satellites. Therefore, the rugged tests to qualify this husky vehicle for spaceflight are correspondingly tougher than any yet devised. Each satellite receives dozens of individual component checks, but the real workout comes in the final step of the checkout. Cradled in the working dolly, the vehicle is plugged into a complex electronic test network in which each part of the system must perform in a simulated flight. For example, a computer sends signals to the guidance and control system that will provide course corrections to the vehicle after it leaves its booster. An intricate web of probes connects each electronic nerve end to the impartial machinery of the analysis equipment. Insofar as possible, the tests duplicate the demands to be made on the components as they are carried along their eventual orbital path. Each operation in the intricate circuitry must perform perfectly in the brief microseconds allotted. Electronically speaking, the vehicle is orbited. Once through this rigid program, the vehicles are ready to move on to the highly critical static firing sequence. Isolated for safety, yet close enough for convenience, the hot firing test stands are located in the Santa Cruz Mountains, a few miles west of the Sunnyvale Development Facility. Here, the satellites, with all pertinent flight equipment aboard, are emplaced in the massive gridwork of the static firing tower. Locked firmly to the earth through tons of steel and concrete, The heavily instrumented vehicles undergo a countdown very similar to the one that will send them into space. Over 15,000 pounds of thrust power briefly shatters the peaks of the mountainside. When once again silence comes, the Air Force acceptance team joins the Lockheed men in a final searching look at the vehicle. Even as this vehicle receives the stamp of approval, another Agena is ready to be mounted in the stand, demonstrating a prime payoff in the system's approach to spaceflight. Following acceptance testing, the satellites are shipped southward to Vandenberg Air Force Base. At this huge Air Force missile launching facility, the vehicles take position with others, awaiting their turn to be thrust aloft. The fact that we have seen a development effort as unique as this in existence implies other things as well. For instance, with the serial production of space vehicles, it becomes apparent that a new capability exists, that of payload versatility. The prime purpose of the Agena vehicle is to provide a space platform upon which to demonstrate advanced space vehicle orbital techniques. In effect, this huge Air Force industrial team has developed a space truck, a vehicle capable of carrying an immense variety of payloads into the orbital environment. Normally, that is the purpose of a satellite launch, to place the instruments on orbit. With the Agena, however, a startling new dimension has been added to the business of spaceflight: to return a capsule to Earth from the orbiting vehicle. The recovery technique was pioneered in the Discoverer program employing the Agena vehicle and accomplished with an especially trained and equipped recovery force. Objects have been returned from space in other programs, but only after a relatively short ballistic course. Thus, one objective of the Discoverer launches is to develop the de-orbiting method for recovery missions. At the launch site, the crew swings into motion as the vehicle, tested, retested, as nearly perfect as humans can make it, is prepared for mating. With infinite care, the satellite is slipped upon the waiting Thor booster. Built by the Douglas Aircraft Company, the Thor was chosen because of its demonstrated reliability. Finally, the payload is positioned. Containing the utmost in skillfully contrived instruments, this capsule is the final part of the combination. Now we are ready. Mated to the boosters, the vehicle and payload are subjected to a seemingly endless series of checks and counter-checks. The Agena-Thor combination lies inert, awaiting the fluids and gases that will flow through the pumps, valves, and lines of the powerful propulsion system. Acid fill lines, vent lines, fuel lines and helium gas lines, nitrogen lines and power cables are quickly, efficiently snugged into place and fastened to the aptly named umbilical mast. Air Force men, Lockheed and Douglas crews move with well-trained precision to perform this complex integrated countdown. From the blockhouse above the launch pad comes the command,
begin task 3, vehicle erection. Begin task 3, vehicle erection.
Ponderously, the liftoff combination smoothly levers upward to the launch position. Approximately 6 hours remain. 6 hours in which the satellite and booster will receive another final component checkout.
Lockheed Launch Console starting task 15, orbital stage guidance and flight control checkout.
Guidance and control circuits, acquisition beacon signals, all the other complex electronics of the vehicle are checked again. T-minus 230 minutes, and the weirdly clothed men of the fueling crew swing into action. Aegena's fuel load consists of inhibited red-fuming nitric acid and unsymmetrical dimethylhydrazine. Known briefly as UDMH, this powerful fuel combines in a controlled explosion with the nitric acid. The combination is known as hypergolic because it ignites spontaneously upon mixing in the engine's combustion chamber. Spotted on the high ground, not far from the waiting vehicle, are the Air Force photography teams. They will provide important photo data for later technical analysis and documentary coverage. Inside the blockhouse, eyes are riveted to telltale gauges, dials, and scopes. As the clock races toward the terminal countdown, the blockhouse activity is the focus of attention of a far-flung network of Discoverer tracking and acquisition stations. At the hub of the Discoverer network is the Air Force Satellite Test Center located in Sunnyvale, California. Tensions are amplified by distance, and the silence is broken only by the impersonal voice of the loudspeaker.
All stations on terminal countdown loop. During the terminal countdown, blockhouse conversation will be limited to countdown items and only
at the launch site, events now flow too swiftly for human control, so electronic devices deftly make the final preparations. All attention is on the clock. Finally,
stations report manned and ready for terminal count. First stage manned and ready.
Orbital stage manned and ready.
T-minus 30 seconds. On my mark, it will be T-minus 5 seconds. Mark, 4, 3, 2, 1, 0.
Ascent trajectory excellent. Downrange radar at Point Magoo locked on and tracking smoothly. Approximately 2 minutes later, booster separation is verified. Seconds later, engine ignition. The vehicle accelerates under rocket thrust to over 26,000 feet per second, almost 18,000 miles per hour in less than 3 minutes. The engine cuts off, and soon downrange radar reports the vehicle is out of range. Almost immediately after the engine is cut off, small gas reaction jets start the satellite into a yaw turn that positions it properly to separate the recoverable capsule following a predetermined number of orbital passes. On the ground, ascent tracking data pours out over the teletype at 100 words per minute to the waiting computer. Converted to the relatively simple language of binary arithmetic, the data is quickly processed. In a matter of minutes, the azimuth, elevation, and velocity data come out of the machine in the form of an orbital plot for the first pass of the vehicle. Now, blinded by the intervening mass of the Earth, radar antennas are pointed hopefully northward, where computer plot indicates the satellite will appear some 90 minutes later, orbiting over the pole. If all has gone as programmed, the vehicle will be orbiting in an attitude 180 degrees from that in which it was injected. At the remote far north tracking station on Kodiak Island, Alaska, the antennas are positioned, alert to the first impulse from the acquisition beacon aboard the satellite. The interminable 90 minutes creep by, and men wait. Far downrange on rocky Kaena Point on the island of Oahu, the 60-foot TLM-18 antenna ponderously turns northward in anticipation of the word from Alaska and the mainland control center that the vehicle is on orbit. Teletype machine ticks patiently. 90 minutes pass. 91. Finally, the control center loudspeakers break their self-imposed silence. Alaska comes in loud and clear.
Dice, this is Cody. Orbital vehicle has been acquired and we are tracking.
Minutes later, Hawaii picks up the orbiting vehicle as it comes within range. The next few minutes in the lives of the Kaena Point men are highly critical. For within the brief span of time that the vehicle can be tracked overhead, they must make contact, read out telemeter data, and make adjustments in vehicle components as directed by command data received from the satellite test center. To demonstrate the recovery sequence, we will witness a recent training exercise. For example, the vehicle will remain on orbit for another 27 hours, or 16 orbital passes, before the recovery sequence will be initiated. During this time, each of the tracking stations will have additional opportunities to make adjustments in vehicle components. This is the period when activity quickens at Hickam Air Force Base, the control center for the Coordinated Air Force Navy recovery operation. Within the bustling center, plotting information is constantly updated. Employing computer orbital information, the Hickam Center will plot the capsule impact area and deploy their forces accordingly. Long before the vehicle was launched from the Vandenberg pad, the Pacific Missile Range Seaborne Recovery Force steams to the planned position to provide backup in the event that the aerial recovery attempt should fail. During the 14th and 15th orbital passes, activity at Hickam builds to a peak as the aerial recovery group make ready. Consisting of 4 RC-121 aircraft and 8 C-119J cargo planes, the aerial recovery group leave for their appointed rendezvous. On the 17th orbital pass, Approximately midway between Alaska and Hawaii, the sequence that sends the capsule earthward will begin. The aircraft swiftly make for the predicted impact area. Back at Hickam Control, the big picture unfolds on the plot board as tracking data flows in. It's now up to the skill of the pilot aboard the pickup plane closest to the descending parachute. For months, these Air Force pilots and crews have trained themselves to a razor edge of perfection in this unusual mission. A tremendous and lonely responsibility rides with the man in the left-hand seat of this C-119. The capsule descends inexorably. The plane is delicately and precisely piloted into place, and contact is made. The skills developed by the recovery team over the months of rehearsal demonstrate that recovery of an object from orbit is both feasible and practical. The Air Force Lockheed team can claim several significant firsts in the advance of spaceflight techniques. Agena is the first satellite ever to be orbited along a precise polar flight path. Out of the first 8 vehicles, all successfully launched, 6 succeeded in achieving orbit. Agena is the first space vehicle capable of performing precise maneuvers while on orbit. Specifically, it can be reoriented to a predetermined attitude along the orbital path and maintained in that attitude until mission objectives have been achieved. Agena is the only space vehicle capable of orbiting a wide variety of payloads. Proved in the Discoverer program, advanced versions of this basic satellite vehicle are already in production for future space programs. Finally, Agena has demonstrated our ability to send various payloads into orbit with a high degree of reliability. The satellite vehicle development within the Discoverer program presents the potential for an endless variety of future space programs and represents an historic step forward in man's eventual conquest of space.